All right, we're still working on circles. We're going to talk about different kind of angles in here, and different kind of lines right here. So this one says the measure of an angle formed by two lines that intersect inside a circle is half the sum of the measures of the intercepted arcs. So in this one right here, what this is saying here is if I wanted to find the measure of angle 1, so this is the measure of an angle formed by two lines that intersect inside a circle. So these two lines intersect inside the circle, is half the measures of the sum of the intercepted arcs. So the measure of angle 1 is half of x plus y. Obviously, the measure of angle 2 would be also half of x plus y. The next one says the measure of an angle formed by two lines that intersect outside a circle is half the difference of the measures of the intercepted arcs. So with this one, if we are outside, what this is saying is the measure of angle 1 is equal to half the difference. Now I take the bigger arc minus the smaller arc. All right, this one says find the value of each variable. So you could probably use these above, you could probably pause the video right now, use these two theorems up above and answer them on your own. Unpause when you're ready. Okay, this one is an outside arc. So 70 should be equal to half of W, the bigger, this is going to be the bigger part, minus 110. I'm going to get rid of the 1/2. I'm going to multiply both sides by 2. I'm going to add 110 to the other side. The other way you could have found this one too is you know that there's 360 degrees in a circle, so you could have just done 360 minus 110. That this was using the above formula. This one is like the first one where they intercept inside. So this angle in here is equal to half the sum of the other two arcs. Again, I'm going to multiply both sides by 2 to get rid of that 1/2. So in this one, x ends up being equal to 40. So this angle over here is, that arc over there is 40. Okay. It says here, a departing space probe sends a picture of Earth as it crosses the Earth's equator. The angle formed by the two tangents to the equator is 20 degrees. What's the measure of the arc of the equator that's visible to the space probe? So basically you have a picture, like here's the Earth. There's these two tangent angles, and they're meeting here at 20 degrees. And you want to figure out what this arc is right here. So again, if you want to pause the video, try to think about it on your own, and then unpause when you're ready for my answer. All right, this is one of those outside angle ones. So 20 is going to be equal to 1/2, but I need to know what this bigger side is right here. What I do know about this bigger side, again, I know the whole circle has to add up to 360, so I do know that this bigger side, it could just be 360 minus x. So if I did 360 minus x is this bigger arc over here, minus the smaller arc. Remember, I'm using this one right here where it's half of the difference. I'm going to, again, multiply both sides by 2 to get rid of the 1/2. I now have, I'm going to move the 2x over here so it's positive. I'll move the 40 over there. Divide both sides by 2. So I get x is equal to 160. Another thing you might notice is that these two right here, when this is outside like this, those two arcs, when they're tangents, that is. So if you have a tangent, these ones will just add up to 180. If it's something like this, where these lines are not tangents, that formula, that idea of 180 does not work. All right. This next one. The theorem, it's kind of funny. So it says for a given point and a circle, the product of the lengths of the two segments from the point to the circle is constant along any line through the point and circle. And the other thing I'm going to tell you to write is I'm going to say point to circle times point to circle equals point to circle times point to circle. I know. That was just brilliant, isn't it? Let me show you what I mean, though. I think that's basically what this theorem is trying to say. I know. And you're still like, what in the world? Okay. So what this theorem again is saying, so for a given point and a circle, the product of the lengths of the two segments from the point to the circle is constant along any line through the point and the circle. So the product of the lengths of the two segments. So again, I wrote point to circle. So if I go point to circle times point to circle is equal to point to circle times point to circle. All right, so that's what that theorem is trying to say, that those products are constant along any line through the point and the circle. So this is one way in which the point is inside. Here's another one, and where the point is now outside. So for this one, point to circle, so point to circle is x, times point to circle, this whole distance right here is x plus y, equals point to circle times point to circle. And then the last scenario is the one in which we have a tangent line and a secant line here, a non-tangent. It's not a tangent here. This is my tangent line. I'll call this one x and this part y. So again, here's the point P out here. That's always been point P there. So point to circle times point to circle. So I end up with t times t, or t squared, is equal to point to circle times point to circle. All right, so those are the three different scenarios you could come up with. So you could pause the video right now and try these next examples here. When you're ready, unpause. So this one looks like this one right here. So point to circle times point to circle, so that's 34, is equal to point to circle times point to circle, that's 16 plus x. Over here, I end up with 476. Here, I end up with 16x plus 256. I do my math here. I get x is equal to 13.75, or if you left it in fraction, it's 55 and a fourth. This one looks like this scenario, so point to circle times point to circle is equal to point to circle times point to circle. This one right here, it's like 42 over 13, which is approximately 3.2131. All right. All right, I'm going to look at two homework problems here. So 20. Whoa. That's what happens when the binder touches my keyboard, or when the book touches my keyboard. All right, so 20. A little bit of stuff going on here in this one. But again, we're just using the same idea here with this point to circle stuff. So if you notice here, we have an x and we have a y. So if I look at the inside point here, I could do point to circle times point to circle equals point to circle times point to circle. So again, I'd have 5x equals to 9y, but that's not really going to help me right now because I can't solve that. So let's look at the other one. So I have point to circle times point to circle, so that's 11 squared, equals point to circle times point to circle. So this one we have 7 plus x plus 5. So 7 plus 5 is 12 plus x. So in this one, what I would do here for this one is I'd distribute that 7 and square this 11. So 11 squared is 121. Distribute the 7. 84 plus 7x. Subtract the 84. Divide by 7. You get approximately 5.286. And then you can take that now, that x, and plug it back in over here. So when you solve that one for y ends up being approximately 2.94. Okay, for 32, we could do y squared. So y, point to circle, times point to circle, is equal to point to circle times point to circle. So right now I wouldn't be able to solve that because there's too many variables in there. But I could also do point to circle times point to circle is equal to point to circle times point to circle. So I can solve this one over here for x, and then I could go back up here and plug that in. And if I do this properly, if you do it without, so if I do 64 divided by 6, I get that 10.666666 repeating. So if I plugged it back in up there, I add it to 6 and I multiply it by 6, I get 100. So it actually works out really well. And then that y squared ends up being equal to 100, so y ends up being equal to 10. So if you don't round it, if you just use the answer button on the calculator, you could have done point to circle times point to circle equals point to circle times point to circle and found that y was equal to 10 that way though too, and that would have been worked just as well. All right, that's it here.